Now, you may wonder why all of a sudden we are talking about complex numbers. Well, you'll see in a moment that we can write down the solutions of wave equations by using the complex numbers. And then it becomes very easy to manipulate those equations. So, let me give a short review on the basics of complex numbers. Now, how do we define complex numbers? If z is a complex number, then we define z to be of the form a plus ib, where both a and b are real numbers. And we define I in such a way such that I squared is equal to minus 1. Now, we can represent this complex number in a diagram which is called the Argand diagram. This is very similar to the Cartesian coordinate system that we regularly use. In the Argand diagram, this is the real axis and this is the imaginary axis. Along the real axis, we plot the real part of the complex number, which is the term that does not contain I, which is a. And along the imaginary axis, we plot the imaginary portion of the complex number, which is simply b here. Now, we can define the complex conjugate of a complex number z, which we denote by z star, as a minus ib if the complex number z was a plus ib. That means all you have to do in order to find out the complex conjugate of a complex number is change the sign of the term that contains the I, that is, the imaginary part. We can also define the magnitude of a complex number, which can be thought of as the distance between the origin of the Argand diagram and the point that represents the complex number itself. So this is the distance we are talking about, which we can call the magnitude. And as you can see, this is simply a squared plus b squared, and we have to take the square root of it. So the magnitude of a complex number, or we can call this the modulus of a complex number, is equal to square root of a squared plus b squared. Now, we can do many operations using these complex numbers. We can add them, subtract them, multiply them, and so on. So, how to add two complex numbers? Well, it is pretty simple. All you have to do is add the real parts and imaginary parts separately, as you can see here. If you just simply multiply these two complex numbers, you will see that it satisfies this formula. Okay. Now, how to take the reciprocal of a complex number? So, if we have a complex number z, its reciprocal is 1 by z. So, it is simply 1 over a plus ib. To simplify this one, we multiply and divide this thing with its complex conjugate a minus ib. And if we do a little calculation, we can show that we can write the reciprocal of a complex number like this. Now let's see what the representation of complex numbers look like in polar form. So let's say we have a complex number z and we represent that complex number in the Argand diagram with this point z. Then this distance from the origin will be defined as the modulus of this complex number, and this angle with the real axis is defined the argument of this complex number. Now, we can rewrite this complex number z using this modulus and this argument. So, As you know, the complex number is a real part plus an imaginary part, right? You see, for this complex number z, the real part is this one, which is simply a cos theta. This is a cos theta. And the imaginary part is simply this one, which is a sin theta. So here is I times the a sin theta. So you see, we can write down complex numbers using these notations. Now, actually, we can rewrite this polar representation of complex number by applying the Euler's equation here. The Euler's formula is that cos theta plus I sin theta can be written as e to the power I theta. So we can rewrite this complex number z as a times e to the power I theta, where a is the modulus of the complex number and theta is the argument. Now, of course, you can prove the Euler's formula by using different methods. You can also Taylor expand this e to the power I theta and see this is actually true. But let us take a different view of this form of the complex number. Let's differentiate z with respect to theta, and if you work this out, you will see that it is simply I times z. Remember, if we are dealing with a times e to the power alpha theta where they're real, then differentiating this with respect to theta would give us alpha times the whole thing again. And now if you differentiate this one with respect to theta, you will get the same result as this one. You can repeat this thing for integration too and see that this result holds. So from this point of view, we see that the complex number can be written as like this. So now let's look at the relationship between this representation and the polar representation of the complex numbers. So the relation between the modulus of the complex number a and b is this one. And the argument of this complex number is simply tan inverse b by a. So this is the polar form of the complex number, and by using the Euler's formula we can rewrite this as this one, right? Now, if this form of the Euler's formula holds, we can ask, what is 1 by z, the reciprocal of the complex number? If this Euler's formula holds and this form of the complex number is actually true, then the reciprocal should be 1 by a e to the power minus I theta, isn't it? Now let's see what the reciprocal of the complex number z, which is 1 over z, looks like in polar representation. So 1 over z is simply 1 over a plus ib, and if we just multiply and divide it with its complex conjugate, we saw that we can write it like this. And for polar representation, let us put the values of a and b in terms of the modulus and argument of this complex number. So we get this cos theta minus I sin theta, and by applying the Euler's formula, you see this is e to the power minus I theta. So actually 1 over z is equal to 1 by a times e to the power minus I theta, as claimed earlier. Now, does that hold for multiplication too? You see, what we have done is just simply multiplied a1 and a2 and multiplied the exponential terms separately, right? And if this form of complex number holds, then it should be true as well, right? We can check that out. So why do we do this? You see, it makes the manipulations of complex numbers easier, right?